This is the famous photo taken 10 years after the accident at the nuclear power plant at Chernobyl. The famous photo shows Artur Kornev, a deputy director, very close, and photographing the largest amount of one of the most toxic and dangerous substances ever made. This substance became popularly known as the elephant's foot due to its resemblance. This substance forms only during nuclear power plant accidents, and a long-lasting core ends up melting. 10 years before this photo was taken, when it had just been formed, it was capable of killing an adult human in less than 5 minutes of exposure. The name of this substance is corium. In over 60 years of peaceful nuclear energy use, there have been just 3 nuclear accidents during which the substance corium was created. They are Eilish, the Chernobyl accident in 1986, the Fukushima Daiichi accident in 2011, and the 3 Mile Island accident in 1979. Very specific and catastrophic conditions led to the formation of corium. In all 3 accidents, the corium remains where it was formed. But what is corium? To understand corium, we first need to know what a nuclear reactor is and how it works, because it is from it that corium is formed. A nuclear reactor is a hermetically sealed cooling chamber shielded against radiation, where a nuclear reaction is controlled to generate electrical energy. Production of fissionable materials such as plutonium for nuclear weapons, radioisotopes for nuclear medicine, propulsion of submarines and artificial satellites, or for research. In simple terms, a nuclear reactor is a machine in which nuclear reactions occur in a controlled manner, with the purpose of producing electrical energy. And due to the nature of such reactions, shielding of the site and equipment needs to be taken very seriously. And it all starts with a large building, usually located near a sea or a river. This building is called the containment building. It is the final physical barrier preventing radioactive materials from entering the environment. This is not just any building or simple building. The thickness of the walls of this building can vary from 1 meter up to 2.5 meters of solid reinforced concrete. In some projects, these walls are double. In addition to the walls, there is an internal mesh of thick steel over 3 centimeters, which helps withstand internal explosions and extreme pressure of up to 5 to 6 atmospheres in some cases. Internally, we reach the structure that makes up the reactor itself, starting with the reactor pressure vessel, which is a huge cylindrical pressure structure that contains the coolant of the nuclear reactor. The core cover in the reactor core. It is one of the most critical and robust components of a nuclear power plant of the pressurized water reactor type, or PWR. It serves to contain the reactor core, where nuclear reactions occur under extremely high temperatures and pressures. It is highly resistant, made of high-quality forged steel, with more than 25 centimeters of thickness and 10 to 15 meters in height. When empty, it weighs more than 500 tons and has an operating pressure of 150 to 170 atmospheres. It is capable of containing the nuclear fuel and the pressurized cooling water, maintaining their integrity under extreme conditions. An important detail is that this vessel is designed to operate for 40 to 60 years. However, it can fail much earlier due to the action of neutrons, intense radiation, chemical corrosion, and thermal fatigue. And if it fails, the plant is shut down. As if that weren't enough, the pressure vessel sits on a structure called the internal containment structure, which is a heavily reinforced concrete safety barrier that houses the reactor and the primary circuit. Along with the reactor vessel, the cooling system, and the external containment structure, the internal containment forms the fourth and final barrier in the defense in depth of a nuclear reactor, being the last stage before the release of radioactive materials in case of an accident. But why so much protection? Why so much shielding? Well, the reason is what happens inside the core of a nuclear reactor to generate energy. Inside the core, there are sets of dozens of rods grouped together, and each of these sets is called a fuel element. In a typical nuclear reactor, there can be from 150 to 250 of these sets, with each set typically containing 200 to 300 rods. Each of these rods is made of a metal called zirconium, which is highly resistant and durable. It has a low capacity for neutron absorption. It is resistant to corrosion by uranium dioxide and only melts at a temperature of about 1,855 Celsius. Inside them, there is the actual nuclear fuel, which can be uranium dioxide and a black semiconductor solid. Or it can be a MOX, or mixed oxide, which is a mixture of plutonium and natural or depleted uranium, which behaves in a similar, though not identical, way to enriched uranium. This fuel comes in the form of small cylindrical pellets, about 1 centimeter in diameter and 1 centimeter in height, more or less, stacked one on top of the other along the rod, which is 4 meters tall. Typically, just one of these pellets can generate energy equivalent to 1 ton of coal, or 149 gallons of oil, or even 17,000 cubic feet of natural gas. That's a lot. And a nuclear reactor typically contains 18 to 20 million of these pellets, and they generate energy through nuclear fission, which is a process in which the nucleus of a very heavy atom like uranium-235 splits into 2 smaller ones when hit by a neutron. In this process, the uranium-235 element is hit and splits, releasing a lot of energy in the form of heat and a lot of radiation. And it gives rise to other elements like barium and krypton. 2 or 3 neutrons are also released, continuing the chain reaction. This splitting releases significant energy as heat. All this heat is used to heat the water in the primary circuit, which is in direct contact with the reactor core. This water is heated to just over 300 degrees Celsius, but it doesn't boil and doesn't turn into steam. Because of a pressurizer that keeps the pressure very high, around 155 bars, it raises the boiling point of the water. This water is used to cool the fuel rods and is also used to heat the water in a secondary circuit, where the water in this secondary circuit boils and turns into steam, and this steam, in turn, spins turbines to produce electricity. It's important to note that the water in the primary circuit, which touches the reactor core and may be radioactive, never directly contacts the water in the secondary circuit. They only exchange heat in an isolated way, in a kind of tube within a tube. And in turn, the water in the secondary circuit boils, turns into steam, and spins turbines to produce energy. It doesn't come into direct contact with the water from the tertiary circuit, which comes from the sea or a river. They also only exchange heat. This way, the reactor becomes much safer to operate. To reduce or even stop the reaction and prevent the reactor from overheating uncontrollably, there is a set of rods that descend between the fuel rods, called control rods. These rods, which are made of neutron-absorbing materials such as cadmium, hafnium, boron, silver, indium, or others, work by controlling the reaction rate if partially inserted, or even completely stopping the fission reaction if fully inserted. Once the neutrons no longer hit the nuclei of the fissile material, the reaction cannot continue. That's the theory, because in practice, atomic physics shows that a small percentage of uranium atoms, when hit by neutrons, do not immediately release all their energy. Sometimes there is a delay, which can be minutes, hours, days, months, or even years. This means that even if all the control rods are fully lowered, reactions inside the reactor can continue to occur and the reactor can keep heating up. And the only way to prevent it from overheating is with the water from the primary circuit. And this explains why used nuclear fuel rods are first stored in large cooling pools for several years. It's because of this strange phenomenon that they keep heating up even outside the reactor. Nuclear accidents occur due to mistakes or loss of control over reactor operations. It could be because there was a lack of cooling water in the primary circuit, or because control rods didn't lower when they were supposed to. Automatic safety system failures, human error, or a mix of these factors. Regardless of the reason, when the reactor overheats too much, usually above 800 degrees Celsius, disaster begins to unfold. Between 1,500 C and 2,000 C, disaster is nearly certain and reactor meltdown starts. At this extreme, the rods containing the nuclear fuel begin to overheat beyond the temperature that zirconium can withstand. From that moment on, the melting of these rods begins, allowing the fuel inside, whether uranium or plutonium, to escape. It mixes with the melted rods. It mixes with the control rods, which also end up melting. It mixes with structural materials of the reactor like steel and concrete. It mixes with water from the primary circuit. It mixes with steam, and it mixes with other elements and materials that end up reacting and forming. In this furnace, extremely radioactive hot lava forms. And this is corium, possibly the most dangerous and most radioactive substance on Earth, capable of killing a human being in just a few minutes of exposure. For example, the corium formed in Chernobyl reached a temperature of about 2,600 degrees Celsius. That's almost twice as hot as the surface temperature of a space shuttle during re-entry into the atmosphere, and half the temperature of the surface of the sun. About 1,500 tons of this material were produced in the accident. Corium forms from the total or partial collapse of a nuclear reactor core. It is a hot viscous mass with the appearance of granules or fragments. It is composed of a cocktail of various chemical elements and materials such as uranium dioxide, plutonium, cesium, 137 strontium, 90 iodine, 131 ruthenium, xenon, steel, zirconium, stainless steel, nickel, chromium, iron, sand, concrete, water, toxic gases, explosives like hydrogen, among other substances. It is extremely radioactive, emitting beta, gamma, alpha radiation and neutrons. It is extremely dense and deadly in direct contact or even at a distance. With a highly variable chemical composition and capable of melting steel and concrete due to its temperature of 2,400 degrees Celsius to 2,800 degrees Celsius. That's what happened in Chernobyl, where the corium formed was so hot that it was able to melt the rods, the reactor pressure vessel, and the thick reinforced concrete floor of the reactor building. And it ended up in the basement. The corium can also contaminate soil, groundwater, and the air for months or even decades. Corium forms in nuclear accidents of level 6 and 7, which are the highest levels on the International Nuclear Event Scale. And, contrary to what our intuition might suggest, after it is formed, corium is a substance that continues to heat up on its own for days, weeks, or even months. This happens primarily due to the nuclear reactions that continue to occur inside it, and also due to the radioactive decay of various radioactive isotopes contained within it. And last but not least, it is also due to the constant chemical reactions of various chemical elements dissolved in this lava, reacting with each other, but also with oxygen and with steam. And it is these uncontrolled chemical reactions that are directly responsible for creating explosions. You may have heard that in the Chernobyl reactor, before explosion, the roof, actually the vessel's lid, was blown off. The reactor containment, which weighed more than 1,000 tons, was blown far away by the explosion. This happened because the water in the primary circuit, which is kept under high pressure, started turning into steam, and the exponential increase in pressure caused the explosion. In other words, inside the reactors, the cooling water in the primary circuit, which is kept liquid at 300 degrees Celsius without boiling, must be kept in that same state. If it turns into steam due to a reduction in internal pressure, it causes an explosion almost immediately. There was a second explosion at Chernobyl, caused by the oxygen in the air coming into contact with the graphite in the reactor, which reacted together and started a fire. And then the air reacted with the water and with the metals in the fuel rods, producing hydrogen, which is an explosive gas. And that caused the second explosion. Although the corium loses heat over time, it remains solid and dangerous for thousands of years, continuing to emit dangerous radiation to any living being and to any exploration robot. In the entire history of nuclear energy production, a total of 5 coriums have been formed. The first in 1979 at 3 Mile Island in the United States, the second in 1986 at Chernobyl, and the third, fourth, and fifth in 2011 at Fukushima Daiichi in Japan, where 3 reactors completely melted down. In all these accidents, the corium was not removed and will remain there for the next several decades.